This is the only photograph ever taken from the surface of a moon in the outer solar system. It looks like a riverbed on Earth, but if you stood here, you would freeze instantly. The temperature is -179 degrees. And those rocks? They aren't stone. They are water ice, frozen so hard they are stronger than steel. On January 14, 2005, the Huygens probe dropped into that orange haze. It landed in the dark. It screamed data back to Earth for just 90 minutes, and then the cold killed it. But what it captured in that brief window changed everything, and the photo of it showed us we still can't explain. The descent camera on Huygens captured a landscape that looked shockingly familiar. Narrow drainage channels branched across brighter highlands, merging into river systems that ran down into lower, darker, flatter regions. There were features that looked like offshore islands and shoals, remarkably similar to those found on Earth. But here's the strange part. None of this involved water. At Titan's temperatures, water is frozen as hard as granite. The rivers and lakes on this moon are made of liquid methane and ethane, the rounded pebbles sitting in that dry riverbed near the landing site. The spectrometer confirmed they were made of dirty water ice, not silicate rock. They were frozen solid, but shaped exactly the way river stones are shaped here at home. And the surface itself was saturated. When the heat from the Huygens probe warmed the soil beneath it, instruments detected bursts of methane gas boiling up out of the ground. The surface material had the consistency of loose, damp sand, possibly the result of methane rain falling on it over millions of years, or liquid wicking upward from below. The dark patches in the images turned out to be organic deposits. Hydrocarbon particles settle out of Titan's atmosphere like a slow, toxic snow. When methane rain washes them off the higher elevations, they collect in the drainage channels and riverbeds, staining them dark. And then there was the volcanic evidence. Scientists found atmospheric argon-40, an isotope that on Earth is associated with volcanic activity. But on Titan, the volcanoes don't spew lava. They spew water ice and ammonia, cold eruptions, cryovolcanoes. So the picture that emerged was this: a world with Earth-like weather and Earth-like geology, but built from completely alien materials. Instead of silicate rocks, frozen water ice. As one of the lead scientists put it, geological evidence for precipitation, erosion, and other fluvial activity says that the physical processes shaping Titan are much the same as those shaping Earth. But the strangest ingredient isn't the ice, it's the sand. Now here's where things get genuinely strange. Cassini's radar uncovered massive dunes stretching across Titan's equatorial deserts. Some are over 90 meters tall. They snake across the landscape in long, parallel ridges, similar in size and shape to the dunes found in Earth's Namib Desert, one of the oldest deserts on our planet. But Titan's dunes have a problem. They point the wrong way. Atmospheric circulation models predict that Titan's prevailing winds blow westward. Dunes are shaped by wind. They should align with it. But the dunes on Titan point east, exactly the opposite direction. And for years, nobody could fully explain why. One explanation involves time. Just like Earth experiences ice ages driven by slow shifts in its orbit, Titan's climate also changes over tens of thousands of years as Saturn's slightly eccentric orbit evolves. A researcher named George MacDonald studied whether these long-term orbital variations, operating on a roughly 45,000-year cycle, could shift the wind patterns enough to reorient the dunes. His results suggested they could. The dunes we see today might be memories of ancient winds, twisted like multimillennial weather vanes. But then, a team at Georgia Tech proposed something much more unusual. They suggested the dunes might be held together by static electricity. On Earth, sand can pick up a slight charge when grains collide in sandstorms. But moisture in the air dissipates it quickly. Earth's air is too damp, and silicate sand conducts electricity just well enough to prevent massive charge buildup. On Titan, the conditions are completely different. There is almost no moisture. The atmospheric pressure is higher, raising the threshold for electrical discharge, and the sand is not silica. It is made of frozen hydrocarbons, tiny pellets of organic compounds, the kind of material that, on Earth, you would associate with mothballs and plastic. To test this, researchers built a small drum lined with hydrocarbon material, filled it with particles of naphthalene and biphenyl, two organic compounds believed to exist on Titan's surface, and spun the drum in a pressurized nitrogen atmosphere to simulate Titan's conditions. The results were dramatic. Up to 5% of the material stuck to the walls of the drum and refused to come out. Particles clumped together. They clung to the container. When the same experiment was run with regular sand and volcanic ash under Earth-like conditions, everything fell out, nothing stuck. The hydrocarbon grains collected up to 10 times more charge per unit of surface area than sand particles on Earth. The researchers estimated that roughly 1/3 of the particles on Titan would carry enough charge for electrostatic forces to dominate over wind. One researcher compared it to opening a box of plastic packing peanuts on a cold day and watching them stick to everything. Imagine your cat getting into the box and the peanuts covering it. That's what is happening with hydrocarbon sands on Titan. A force we don't normally think about on Earth is having a big impact on the landscape in a way that isn't very intuitive. In that scenario, only Titan's fastest winds, stormy gales that might periodically blow in the opposite direction during major seasonal shifts, would have enough force to sculpt the dunes. The rest of the time, the sand just clings together, holding its shape, resisting the wind. If you grabbed a pile of this material and built a sandcastle on Titan, it would stay standing for weeks, maybe months. The researchers also realized something else. If electrostatic charging occurs between microscopic particles of smog high in Titan's atmosphere, the particles could glom together, grow, and fall to the surface. Which means the sand on Titan might not really be sand at all. It might be closer to snow. Frozen, charged, hydrocarbon snow that piles up into 100-meter dunes and refuses to move. But the strangest thing on Titan isn't the dunes. It's something that keeps appearing and then disappearing, and for years, nobody could explain what it was. In Cassini's radar images of Titan's northern seas, scientists noticed bright spots on the surface of a hydrocarbon sea called Ligeia Mare. This is a body of liquid methane and ethane, roughly 420 kilometers across, with shorelines stretching over 2,000 kilometers. Dozens of rivers drain into it. It is the second largest known body of liquid on Titan. And in 2013, something appeared on its surface that wasn't there before. A bright feature, roughly the shape of an island, visible in the radar data. Scientists looked. It was there. They looked again. It was gone. Then it came back. Then it vanished again. The features would appear and persist for a few hours, sometimes weeks. Then nothing, as if the sea had swallowed them whole. Scientists called them magic islands. Islands don't just vanish. Land masses don't flicker in and out of existence. But on Titan, something was doing exactly that, and nobody could figure out what. Were they real, physical objects? Were they phantom echoes from waves on the surface? Some researchers proposed they might be chains of nitrogen bubbles fizzing up from below, like a champagne glass on an alien sea. For nearly a decade, the Magic Islands remained one of Titan's most unsettling mysteries. Then, in January 2024, a planetary scientist named Jinting Yu at the University of Texas at San Antonio published a study that offered a compelling answer. She had been looking at the relationship between Titan's atmosphere, its liquid lakes, and the organic material that snows down from the sky. Titan's upper atmosphere is dense with organic molecules. They clump together, freeze, and fall to the surface, including into the lakes and seas. You wanted to know what happens when that frozen material hits the liquid. Does it dissolve, sink, float? Her team found that the lakes are already saturated with organic particles, so the falling material would not dissolve. But methane and ethane have very low surface tension, making it hard for solids to float. Most of the frozen organic material would be too dense to stay at the surface, unless it was porous. If the clumps had a honeycomb-like structure, full of hollow spaces and narrow tubes, they could float. Liquid methane would slowly seep into the pores over time. Eventually, the clumps would become waterlogged and sink. That would explain both the appearance and the disappearance. Individual clumps would be too small to show up on radar. But if enough of them collected along a shoreline and massed together, larger chunks could break off and drift across the surface, like glaciers carving icebergs into the sea on Earth. Only here, the icebergs are made of frozen organic snow, and the sea is liquid natural gas. So the magic islands are real, not waves, but rafts of frozen, porous, organic snow, drifting across an alien sea and slowly sinking out of sight. Yu's work also helped explain another mystery. Why are Titan seas so unnervingly smooth, with waves only a few millimeters tall? A thin, floating skin of frozen organic solids on the surface could suppress wave formation entirely. A frozen blanket on a methane sea. Now, everything we've talked about so far has been happening on Titan's surface. But the deepest mystery might be what lies beneath all of it. For nearly 2 decades, scientists believed Titan had a vast ocean of liquid water hidden under its frozen crust. The evidence came from Cassini. As the spacecraft flew by Titan, researchers tracked its radio signals to measure changes in the moon's gravity field. They found that Titan flexed significantly under Saturn's gravitational pull, stretching and compressing as it orbited. The amount of flexing suggested something liquid was sloshing around inside. Think of a balloon filled with water compared to a billiard ball. The balloon deforms easily. A solid sphere does not. Titan was deforming more than a completely frozen body should. That measurement, published in 2008, was taken as strong evidence of a subsurface ocean. It shaped our understanding of Titan for years, until someone went back and listened more carefully to the data. In December 2025, a team led by Flavio Petrica at NASA's Jet Propulsion Laboratory published a study in the journal Nature that changed the picture entirely. Petrica's team reanalyzed the original Cassini radio tracking data using a new processing technique that reduced the noise in the measurements by roughly 25 to 30%. What emerged was a signal that earlier analyses had missed. Titan's shape-shifting lagged about 15 hours behind the peak of Saturn's gravitational pull. That timing was the key. Moving a thick, viscous substance takes more energy than moving a free-flowing liquid. It's the difference between stirring honey and stirring water. By measuring the delay, the researchers could estimate how much energy Titan absorbs as it deforms. The result was surprising. The amount of energy being dissipated inside the moon, roughly 3 to 4 terawatts, was far greater than expected if a global liquid ocean were present. A liquid ocean would actually reduce the tidal dissipation generated in the layers below it. The numbers did not fit. The researchers ran 2 sets of models, one with an ocean, one without. Only the models without an ocean matched both the degree of flexing and the energy dissipation signature in the data. So what is actually down there? The study proposes layers of solid ice overlying a thick region of slushy, high-pressure ice closer to the core. This slush sits near its melting point and is being intensely heated by tidal friction. Its viscosity is low enough to allow strong convection, meaning material from the rocky core can be transported upward through the slushy layers toward the surface. And within that slush, there are pockets of liquid water, some potentially as warm as 20 degrees Celsius. That's about 68 degrees Fahrenheit. Room temperature, not a vast ocean. More like Arctic sea ice or underground aquifers. A network of warm, pressurized water pockets threaded through a matrix of slushy ice, cycling nutrients from the rocky core upward through the frozen shell. The measured tidal dissipation also revealed something about Titan's history. The amount of orbital energy being lost means Titan's current orbit around Saturn cannot be ancient. Its eccentricity should decay to zero in roughly 30 million years. Something happened relatively recently, in cosmic terms, to put Titan on its current path. Some researchers believe the loss of another moon in the Saturn system within the past 100 million years may have perturbed Titan's orbit. As Petricca put it, nobody was expecting very strong energy dissipation inside Titan. But by reducing the noise in the Doppler data, they could see these smaller wiggles emerge. That was the smoking gun. Now, this might sound like bad news. If there's no ocean, doesn't that reduce the chances of finding life? Actually, it might improve them. In a vast ocean, nutrients and organic molecules would be diluted across an enormous volume of water. But in small, concentrated pockets, those same nutrients become far more available. The warm water pools inside Titan could be enriched by organic molecules supplied from below, from the rocky core, and from above, delivered by meteorite impacts on the surface. Titan's atmosphere already contains a diverse range of organic molecules: nitriles, hydrocarbons, benzene. Organic chemicals essential to life on Earth, like nitrogen and carbon-based compounds, are found on and around Titan in abundance. The researchers compared the potential environment to Earth's polar sea ice ecosystems, one of the largest biomes on our planet, where a surprising diversity of organisms thrives despite extreme salinity and near-freezing conditions. And the volumes involved are not small. Titan's hydrosphere is enormous. Even 1% of it being partially melted would equal the volume of the entire Atlantic Ocean. 0.01% would match the Mediterranean Sea. Nobody expects to find anything swimming through slushy channels beneath Titan's ice. But as one researcher noted, while Titan may not possess a global ocean, that doesn't preclude its potential for harboring basic life forms. In fact, it might make Titan more interesting. So here we are. A moon that looked like nothing through a telescope. A world that revealed itself piece by piece over 2 decades. And every answer it gave us brought another question. Rivers that flow with liquid methane but have barely eroded the landscape. Dunes made of frozen plastic held together by static electricity. Islands that appear and disappear on alien seas. And an interior that turned out to be not an ocean at all, but something stranger, something slushier, and possibly something more alive than anyone expected. NASA's Dragonfly mission is expected to launch in 2028, a car-sized rotorcraft drone, the first of its kind, designed to fly across Titan's surface. It will sample the organic material on the ground. It will study the chemistry. It will carry a seismometer that could probe the interior and test whether the new ocean-free model holds up. And maybe, just maybe, it will find something no one predicted. Because that is what Titan does. Every time we think we understand it, it changes. Every image raises a new question. Every answer reveals something deeper. It is a world built from the same physics as Earth, but assembled with entirely different ingredients. A place where it rains gasoline and snows plastic, where the rocks are made of ice and the sand is electric, where islands are made of frozen sponge and the ground beneath your feet might be hiding warm pockets of water just a few degrees cooler than a swimming pool. We have been staring at Titan for 400 years. We have only been seeing it clearly for 20. And the more we look, the stranger it becomes. For now, all we can do is watch and wait and wonder what the next image will show us.